his valuable knowledge and insight. Thank you, sir.
Yeah, thank you for a nice introduction, please. Thank you. Okay, so today the topic which I'm going to discuss or present from my side is the resilient GNSS. So what are the signal processing strategies that are there to detect or mitigate the jamming and spoofing, which are the main vulnerabilities in GNSS systems? Presently, I'm at Tampere University as a postdoctoral research fellow. Is it audible to everybody?
Yeah, audible, sir, but
Yeah.
the PPT is not shared.
It is not?
PPT is not shared yet.
It is not shared slides?
Yes, sir.
Oh, 1 minute. Actually, I shared 1 minute. Okay. Now you can see?
Yes, sir.
Is it visible now?
Yes, sir. Yes, sir.
Okay, thank you. Yeah. Yeah, the present topic which we are discussing is on the resilient GNSS. So GNSS has got some vulnerabilities. That means the GPS signals, what we are called, have been having a threat because of two major activities. One is called as jamming, and another one is called as spoofing. So in this lecture, we just see in this presentation what are the signal processing strategies that are applied for detecting jamming and spoofing in GNSS signals, and how a resilience is improved for a secured navigation. So the content I have framed in such a way that I'll give some brief introduction about these GNSS systems, an overview, and then what are the GNSS receiver measurements that are typically which are used as the key performance indicators when there is a jamming and spoofing event. And just I'll try to introduce what is actually the jamming is and what the spoofing exactly in case of spoofing and how it is defined as spoofing activity, and what are types of spoofings that can be carried out and how do they are detected, and what general mitigation strategies that they have been applying for that, and in similar way for the GNSS jamming also. So we see what are the types of jamming that can be carried out and how you can detect the jamming and how do you mitigate the jamming, and some current advancements and emerging trends of algorithms just we discussed as in the direction of research how it is going on currently for these kind of uh, vulnerabilities and how new algorithms are being evolved or how they are being improving the resilience in the systems through software or hardware or at different levels. So, from the signal processing point of view, we just discussed some of the points in this direction also. So as you are aware that GNSS positioning, so you might have already understood it's a trilateral principle. That means a minimum 4 or more than 4 satellites are required to determine the position. And there are many errors in the satellite signals. That means the satellite signal, when it is propagating from the satellite to the receiver, it will undergo some impairments because of the atmosphere like ionosphere and troposphere. And when it reaches to the earth, because of the urban air environment or the surroundings, there will be multipath. And other than that, there will be clock biases because the satellite clock which you use is high precision, and at the receiver level you use a normal clock, so the bias will be there. So which requires a precise timing for calculation of the pseudo range, which in turn is required to determine the position, because position estimation is carried out with the help of the pseudo range determination from the satellite to the receiver and the satellite positions. So like that, we have 4 or more measurements from the satellites. You can easily determine through a least square solution the position of the user. And coming to the GPS systems, there are different types of GNSS systems that are developed by different nations, like GPS of US, Galileo, okay, and Russia has got its own navigation system called as GLONASS. Like that, every nation is being developing their own satellite-based navigation systems. Apart from that, for civil aviation applications, because this navigation concept or the GPS is primarily used for military purposes, and for the civilian purposes also you are using for precise timing and positioning. Where aircraft navigation is one such example where we use these GPS corrections for the aircraft when it is moving from one place to another place through its operations like in phase and route and landing purposes to attain the accuracies. Like that, there are some satellite-based augmentation systems where the GPS corrections are provided through geostationary, and there are different types of satellite-based augmentation systems, which you might have already gone through this kind of things in the previous lectures. So this is just an overview of the map that shows what are the different types of SBUS systems that were deployed around the world. Now, and you understand that now we will likely go into the signal processing aspects because the jamming and spoofing are very much related to the signal processing at the signal processing level, that we have to understand what happens when the jamming or spoofing is happening. And you are all aware that the GPS satellites or navigation satellites which we are using are generally are at the height of MEO, which is called as medium earth orbit, typically around 20,000 kilometers from the surface of the Earth. So various systems will deploy either 3 or 6 orbital planes in which the satellites are placed actually. So a minimum of 24 satellites are required to have anytime 4 satellites in a view for the user, one who is using a GPS system on the Earth. Now when it comes to the GPS receiver side, so the GPS receiver generally a typical diagram here I have shown here where the GPS receiver what it does here is that it will acquire the GPS satellites and it will start doing the tracking. These are CDMA based satellite signals. So there are co-tracking and carrier tracking that is widely used in this because the signal is uh, BPSK modulated or binary offset carrier modulated. For different systems, there are different types of modulation schemes. These are a couple of modulation schemes that are used here majorly. And the code, that means C by A code, course equation or P code, that is nothing but plus or minus ones like this, which you can see here on the top right side. So this code is modulated onto the carrier phase. And a data navigation bits like satellite ephemeris information also is modulated onto this signal. So this is despreaded or demodulated at the receiver end. Okay. And there are different types of, since there are different types of systems, there are different types of signals that also that are transmit, like GPS will transmit on L1 and L2, and there is an L5. Similarly, other systems also E1, Galileo is represented by E, GPS signals are represented by L, and BIDO of Chinese system like GPS, it is different, that signals are represented by B1, B2, B3, and GLONASS G1, G2, G3. Okay, so these are the different frequencies. Typically, it is 1 to 2 in between gigahertz actually. Now, coming to the GPS receiver, this is the primary part that we have to understand here technically at the signal processing level or that at the measurement levels. What are the measurements that will get affected when that happens, jamming or spoofing? Generally, at the receiver front end, you will measure something called as AGC count, that is called as automatic gain controller. Depending upon the signal received signal power, this AGC or there will be an automatic gain control instrument that will control the voltage inside, and we can derive a count from that, which is called as AGC count. And this one it is called as automatic gain controller. This is one of the measure. That is next one is the noise floor at the RF front end level, which we measure. And that RF front end level signal which you receive is at 1575 megahertz. Typically, if you think that it is an L1 signal, so it is converted into an IF frequency at the receiver, some intermediate frequency like 38 megahertz or so, and then it is digitized. So when it is digitized, you will get the IF samples, okay, IQ samples, and then happens the signal acquisition where each signal has to be correlated. First, you have to understand the signal. Each satellite, since it is a combination of multiple satellite signals that are being transmitted, each satellite is identified by a specific code. That code is generated internally and is tried to correlate with the incoming codes of the satellite signals, and whether this matches a particular satellite is identified, and its code and carrier are being tracked in the tracking loop. At the tracking level, you will see DLL, PLL, discrete delay local loop and PLL local loops, discriminator outputs, and here you will measure the carrier to noise ratio. And after that, navigation decoding is done. And finally, PVT, navigation decoding, is to determine the satellite positions. Keplerian elements were derived and to determine the satellite position. And from this tracking loop, you'll try to continuously track with the help of DLL and PLL, you'll try to track the satellites that are identified in the equation. And finally, from those measurements, you'll try to find out the position, velocity, and time. So now you have to be very keen about this AGC outputs and DLL and PLL and C naught when we are very much specifically talking about your jamming and spoofing. Now, what is DLL and PLL is nothing but, as I said you, the incoming signal should be correlated. So there is something called as early and late correlation that is carried out within the receiver. That is early, prompt, and late correlators are there within the receiver. The signal is nothing but the signal contains this code, either plus or minus one sequences. So this is correlated with the help of the correlators. So how much the signal is exactly matching with the incoming signal. The internally echo, the same signal is generated and the code is correlated to identify a particular satellite. Whether the code is exactly matching, if it is prompt, if it is by 0.5 chips, it is like this. Okay, early. If it is late by 0.5 chips, it will be like this. So by taking the difference of these things, we'll try to find out. We see that it is promptly aligned. So this is what which happens in the DLL. When it comes to the PLL, it's like instead of having an early late, PLL will have in phase and quadrature phase correlators. In phase is cosine and quadrature phase is a 90-degree phase shift. Okay, from it, the receiver computes the phase error and adjusts the local oscillator to reduce it, and it keeps the loop locked. So this is the basic functionality of the DLL and PLL in the receiver to track the carrier phase and code phase in the receiver. So this is the basic diagram how these DLL and PLL were carried out and the internal structure of this GPS tracking system actually. Okay, so any GNSS system will have such kind of functionality. It's very much similar. Now, coming to the GNSS vulnerabilities, jamming and spoofing. What is jamming and what is spoofing? As you can see in this figure, jamming means transmitting a high power signal within the band or to the near band of the GNSS signal. Okay, GNSS signal operates in L band. If you're transmitting a signal which is very much within the band of L band, so and having a higher power, then it will interfere with the signal which is received by the satellite at the receiver. Then it is called as jamming. Jamming can suppress the satellite signal. So the receiver may not able to track those satellite signals because satellite signals become very weak such that this interfering signal will try to jam it. As the word says, it will jam and there is no further way to track these signals. Sometimes if the interference is weak, the receiver signal may its carrier to noise ratio will try to reduce than the original signal, but you could able to have the signal with varying C by a naught. Okay. Now, when it comes to the spoofing, spoofing is nothing but transmitting a signal like a GPS signal from a transmitting antenna with any type of with a different way of generating there are different ways of generating the GPS signals such that the receiver will think that one which is coming here which is generated is an original signal. It assumes that it is an original signal and it will try to get delocked with the actual signals coming from the satellite. So this spoofing signal can have the characteristics in such a way that when the receiver gets locked onto this signal, the spoofer, one who is transmitting this kind of signal, will try to manipulate the receiver functionality, or the signal will be in such a way that the receiver can, when get locked, it mislead and give a different types of positioning information, okay, than actual original position that it has to provide. So this is called as spoofing. So one is called as jamming and another one is called as spoofing. Okay, so because of the spoofing, if you see on the right hand side the picture here, the spoofer, one who is transmitting this kind of signal, instead of a receiver to determine the real position, it will try to determine a position which is different from the actual position. That is called as spoofing. Now, what is the spoofing threat? So as the definition goes, in a GNSS spoofing attack, the advisory referred to as spoofer, the person one who wants to send a spoofing kind of signal, will try to mislead the receiver by transmitting a counterfeit GNSS signal known as spoofing signal. Known as spoofing signal. So by transmitting the conversation known as spoofing signal, so that the receiver computes an inaccurate position, velocity, and time PVT solution. So what happens? Actual received signal will not only have its original signal, it will also receive the spoofed signal. When the spoofed signal get attached to the original signal, this spoofed signal overrides our original signal, so that the receiver will start getting locked onto that, and it will start tracking this RSFT. There are different approaches of doing the spoofing: simplistic method, and intermediate spoofing, and a sophisticated spoofing. In simplest spoofing, they will use a GNSS simulator, okay, to generate a GPS like signal and to transmit. In intermediate, they will use a receiver, okay, with sometimes multiple antennas also. A sophisticated will use a different higher approach where there are multiple receiving receivers transmitting the GPS like signals to the person, to the victim receiver. Actually, here the mobile is the victim receiver. Okay, now we see one by one what are the spoofing generation techniques that were there. So in GNSS signal simulators, generally the simulator is capable of generating the GPS kind of signals. Actually, there are different types of simulators that are openly widely available in the market. Even an SDR, software defined radio, with the help of a MATLAB code or through a Python code, that can generate a GPS kind of signal which can be associated with an antenna and transmit the GNSS like kind of signal. Okay, so uses GNSS signal simulator plus RF transmitter, because this signal has to be transmitted to the victim receiver. Okay, so in general, in this kind of thing, the signal which is transmitted will where the for example a mobile phone is tracking the GPS signals. I want to spoof that mobile. So what I will do is that with the help of a simulator, I will try to spoof a GNS kind of signal and I will try to transmit to the mobile. So the mobile will start, but anyhow, my signal which I have transmitted is not very much synchronized with the one, though it is a GPS kind of signal, it will not get so much synchronized with one which is receiving. So, so what happens is that this signal, when it is being detected by the tracking loops or trapping loops within the receiver, it will start get tracked because of the signal power. It may start tracking, the mobile phone will start tracking the spoofer signal, and the peaks of this signal are misaligned with the authentic signal, so it appears as a noise in the tracking mode. So now this kind of spoofing will disrupt the equation process, and it may be appear as a noise in the tracking loops. It can impact worsen if spoofing power is more than authenticated signal. And so how do you detect that? Since the transmitted signal can have an amplitude variation than compared to the original signal, so you can you can monitor the amplitude. You can monitor the amplitude, or you can cross check between the measurements, DLL and PLL measurements, to determine whether any spoofing activity is being carried out. Okay, and additionally, if your mobile phone is having an IMU that also provides the position velocity time, the spoofing activity will change the position velocity and velocity of the user. So you having the IMU position velocity and time, and the spoofed position, you may correlate both of things and you can identify whether a spoofing activity is carried out or not. So the other way of doing spoofing is that instead of using a simulator, we will use the receiver itself. Okay, a spoofer also can have a receiver. With that, he will try to generate the signals, spoofing signals. Okay, that means here if you see the diagram, there will be authentic signal received by the receiver. From this, he will try to again retransmit these signals. It looks more like an authenticated signal. Actually, the target receiver is already receiving the authenticated signals from the satellites. This signal will just go and coincide with this, and the target receiver will get locked with these signals. Okay, then what happens when both are seeing the same satellite signals and they are transmitting? If in the transmitting process, if we increase the transmitting power of the signal gradually, the receiver will try to track it at the receiver. The target receiver will start locking onto this spoofed signal than the authentic signal actually. So what happens is that here you can deceive the tracking receiver, not just equation, but also at the tracking level completely. And also you can simulate the position, time, and satellite ephemeris from the here from the swooper side actually. So the main challenge is projecting spoofed signal with correct delay and power. Okay, So if the major challenge here is that the spoofing signal which we are generating should be correct in delay. What is correct in delay means, as I already shown you, this one. The correlation between our spoofed signal and the authentic signal, if they correlate exactly without any prompt delay, okay, then the tracking receiver will straightforwardly will take the spoofed signal. So that is the challenging, how much correct delay that has to be generated so that it will coincide more with the authentic signal. And if the power is more than this, automatically the receiver will track this and will leave the actual authentic signal. Okay, so this is the repeater spoofer architecture. This is called as. And next one is sophisticated receiver based spoofer. As I told you, there are three types of spoofing. This is a sophisticated one. So in the sophisticated one, most complex and effective spoofing method, this is assume entry level of victim receiver antenna position. If for this, the victim antenna receiver antenna position has to be known at the centimeter level, and we should able to perfectly synchronize the code and carrier phase of the authenticated signals. We use multiple transmitting antennas, not single transmitting antenna like this, but multiple receivers with multiple antennas to target the other victim receiver. And there are angle of arrival based anti-spoofing techniques that are there. When you use this kind of sophisticated receiver based spoof, or even that kind of techniques cannot able to detect the spoofing activity actually. Okay. So next one is one type is called a spoofing based on receiver state. What exactly this mean is that satellite navigation receivers exhibit different levels of vulnerability to spoofing attacks depending upon whether they are in acquisition phase or in the tracking phase. For example, where you have a GPS receiver and you have two types of things for the GPS receiver. One is called as a cold start, another one is called as the warm start. So cold start is that where the GPS receiver is power on just now, where the GPS receiver don't have any information of any satellite ephemeris at all to determine its position. It takes time for the satellite to acquire the satellite signals and determine its position from the satellite positions and pseudo ranges. That is called as cold start. So in that scenario, receiver cannot differentiate between the spoofed versus authenticated signal. Suppose you have started a receiver and there is simultaneously a spoofer, one who is transmitting the signals, and the receiver will start tracking both the authenticated and spoofed signals also. If they are very much similar, then there is a very likely more chance that it cannot at all differentiate between the spoofed and authenticated signals. So even if partial data exists like almanac, last position or time series within next 30 seconds or 40 seconds that which you acquire, okay, that may not be very much easy for detecting the spoofing is kind of scenarios actually. Okay, so a receiver can be misled very easily during the initial acquisition stage itself when it is a cold start. Okay. Suppose it is not the cold start. Okay, you have started the receiver and spoofing activity has started before later after some time. So what happens? It will transmit a GPS like of signals which are like which are not authentic, but the receiver will start. But the receiver will have some prior knowledge of all the signals it is acquiring. So when it is when something goes wrong and it will start reacquiring the spoofed signals with the prior knowledge of the data of satellites or the position, it can be detected very easily. So then the position estimates which you have already carrying out, okay, forms as a lace as a basis, and when a spoofed signal is transmitted, it will give you a position. You can compare with your previous position, can at least determine how much it is getting deviated from the previous position, or how much the manipulation of the position is being carried out. In that way, you could able to detect this type of spoofing. And next one is spoofing during tracking. So now the satellite started acquiring the signals and it is also started tracking the signals. So most challenging scenario for the spoofer is fake signals must remain synchronized with the receiver physical movement. Okay. So that means the tracking loop will track the satellite signals which are having a high correlation, okay, with respect to the internally generated the code or carriers, okay, and it once get locked into with the help of your early late and prompt DLL and PLL, IQPLL, okay, which perform this operation actually. So most challenging scenario for the spoofer is fake signals must remain synchronized. That means that the spoofer one who is transmitting the signal should able to synchronize exactly with the original signal. Then only the tracking loop will take these signals and may avoid taking the other signals. So this high precision signal generation of spoof signal is required in this case. So based upon the receiver state, whether you are doing it before just before you started doing spoofing before the receiver starts, or at the initial periods of equation, or when the receiver is active and it is start tracking and it is continuously being acquiring, and in between you have to do spoofing. So depending upon the state of the receiver, spoofing, how the spoofing detection or the spoofing to be carried on out in its complexity will increase. Okay, now we will see at what levels the spoofing attack can happen and what are the types of spoofing attacks that can happen. Spoofing seeks to mislead GNS receiver position and time. What majorly is that the time determined by the GPS receiver is have to be spoofed and the position has to be spoofed. That means actual position, if it is determining some x, y, z value, it has to show some x1, y1 and z1 which is different from x, y, z actual position. So this can happen by manipulating the ranging codes and navigation data. Okay, these are the major things which I told, that the GPS signal consists of the ranging codes, C by A codes or P codes, and the navigation data. So if you could able to manipulate these two things and transmit a signal so that the receiver, if the receiver tracks those things instead of the original one, it will get spoofed. So at the signal processing level, modulation, PRN codes, frequency, bandwidth, Doppler range, signal strength, etc. are publicly known actually within the receiver. With this knowledge, a spoofer can generate the counterfeit signal resembling the alternate GNS signal. So whenever a signal has been generated, see for example, when you are transmitting a GPS signal structure is already well defined with all these things. So since the spoofer, if he can understand the characteristics of these signals, he will try to generate these kind of signals similarly and try to retransmit. Okay. By tuning these parameters, the spoofer can effectively deceive the target receiver. Next one is at the data bit level. So spoofing activity types, this is the another one, which is a data bit level. Here what happens is that navigation data. What the navigation data consists of? Satellite ephemeris, that is the Keplerian parameters of the satellite. If you could able to manipulate these ephemeris data and transmit, because you know that these ephemeris data will be for acquiring the ephemeris data in a signal, it requires only less than 1 minute by the GPS receiver, and they remain constant till up to 12.5 minutes for any particular satellite. So if you can able to manipulate these things, okay, then easily if the satellite positions are manipulated, that means if you manipulate the Keplerian elements and if you transmit from a spoofer device, if the receiver start taking that kind of signal, then the satellite positions are different from the original satellite signals and their positions which you are receiving, and automatically your pseudo ranges will differ and your position will vary. So this is how this kind of spoofing attack can be carried out. The other one is at the data level, one is at the signal level. Next, so these are the two main types where how you can do the spoofing. Now, how the spoofing will happen and what are the different types of spoofings that are carried out. So, multiple variants of spoofing attacks can arise depending upon the operational state of the receiver. There are different types of spoofing attacks that are there. One is called as a lift-off delay attack. So, what exactly happens in this is that, see, if you see the figure here, the black triangle here that represents is the original signal. The other one is, the red one is the one which is the spoofing signal that is transmitted. Suppose these, if you think that these are C by A codes, I am transmitting the bits to correlate. At time t0, it is like this. Time t1, a slightly improvement in the amplitude with some delay difference. And after that, I have slightly improved the amplitude of the signal. with a different delay. And finally, in such a way that I am transmitting a signal with varying delay and with varying amplitude, slightly increasing the delay and amplitude. So in that fashion, if I am transmitting a spoofing signal, if the receiver one which is receiving the original signal, here the black one, if my transmitting spoofing signal whose signal characteristics correlates with respect to the similar delay and amplitude, and then when with that same delay or with a slight difference, if a little bit more amplitude, if I could able to transmit the signal, the receiver will start tracking this signal. That which here we can show that, tell that it is happened at the time interval of t is equal to t4. So in this, what happens is that, the time delay which I'm introducing will become zero when it becomes very much equal to the original signal. Okay, and spoofing amplitude will be very much equal to the authentic signal amplitude. When I slightly exceed beyond that, the receiver will start taking this kind of signal. Okay, so this is called as lift-off delay attack. Lift-off delay attack. That means you are changing the delay of the signal to correlate with the original signal. Okay, as much as possible. And lift-off aligned is a similar to the lift-off delay, but spoofer stays aligned with the line of sight signal. That means delta TS is equal to 0. Here they maintain the alignment using spoofing amplitude and authentic signal both have the amplitude same. Okay, then initiate the lift-off. So advantage that avoids the detection far from the prompt correlator. Drawback is main cause abrupt changes in tracking parameter if spoofing appears suddenly. So receiver is more vulnerable. Okay, during signal acquisition, this happens during at the signal acquisition level, during tracking with self-spoofing devices. So this lift-off aligned can be carried out during signal acquisition and tracking stages of the receiver. Now, another one is called as mechoning. Okay, here in mechoning, what happens is that you'll try to delay the signal of the GPS signal and transmit to the receiver. Okay, so what happens is that you are receiving some GPS signal. As a spoofer, what I will do is that I will receive the GPS signal and I will try to delay that with some time interval and I will retransmit to the receiver. So the receiver, when it starts locking onto that signal, because it's a GPS signal, but it is delayed with some time interval than the original signal. So victim receiver locks onto the delayed spoofed signals and computes the false position, location of the spoofer antenna. Okay, so powerful method can spoof any GNS signal, even encrypted military signals also can be done with the help of mechoning actually. And next one is jam and spoof attack. Jam and spoof effect is nothing but, as I told you in the beginning, there is a jamming effect and spoofing effect. So far we are talking about different types of spoofings. As I said to you about jamming, you will transmit a high power transmitting signal. So all the signals of the GPS receiver can be jammed. Then I will start using a spoofer. So the receiver will start taking my signals, okay, than the satellite signals, because all the satellite signals are jammed because I have transmitted a signal which is at little bit higher power where all the satellite signals are jammed. Okay, but the spoofer will transmit a signal which is much higher than this jamming signal power. So the receiver, thinking that it has a GPS signal, it will start taking the signal. So this is called a jam and spoof attack. So like that, these are the different types of spoofing attacks that can be performed at different levels at the acquisition or the tracking level and make the victim receiver affected because of the spoofing. And next one is the non-line of sight spoofing. Commonly that happens in the urban areas, because in urban areas not all the time the GPS signals can be tracked continuously. When there is a when you are going between the high raised buildings with your in your car with a GPS receiver, sometimes satellites which are above the horizon only received and some of the satellites which are at low elevations get continuously blocked. So the GPS, the spoofer can also have a GPS receiver in one of the buildings and can understand that these are the satellite signals that have been missing to the receiver, and he can generate such kind of GPS signals which the GPS receiver is missing, and in that way he can start doing the spoofing activity. So there are different ways how this spoofing attack is being carried out. So far we have seen what is the spoofing and how the spoofing is being carried out. Now we will try to understand what are the countermeasure techniques that we can do. Actually, what is countermeasure is that first the receiver should be able to detect the spoofing, and next it should be able to mitigate it. Okay, so detection means first you have to identify that someone is trying to send a false signal. You should be able to find out that this is not the actual GPS signal, there is the false signal. That is called as detection. Once you identify that is a false signal in the receiver, you should be able to include a functionality such that instead of tracking the false signal, you try to start, because once the receiver gets locked onto the false signal, you should be able to understand that it's a false signal and get back to your original signal. You have to discard this false signal and be able to receive the actual original GPS satellite signal and track it. So this is what actually how to do here. That is called as spoofing detection. One is called as spoofing detection, another one is called as spoofing mitigation. Spoofing detection focuses on identifying the spoofing signals, uses algorithms to discriminate authentic and versus counterfeit signals, and does not necessarily neutralize or remove the spoofing attack. When it comes to the spoofing mitigation, focus on counteracting the spoofing after detection. Techniques aim to neutralize the spoofing signals and helps receiver recover accurate position and navigation capability. So anti-spoofing techniques, a multi-layer perspective is there or that can be implemented here as well. One is called as a signal processing level technique. So in signal processing level, data bit level, because I told that there is signal processing level spoofing attack, data bit level spoofing attack that can be happened actually. First, when I am trying to tell. And next one is that because of spoofing activity, what happens? Position solution or position solution get uh, deviated. So what are the other assistance or process other consistency checks that can be carried at the position level is with the help of using IMU or Wi-Fi or cellular positioning, that which we can use to see the authenticity of the position we are getting when a device is under spoofing. Okay, so signal processing level techniques applied at the antenna level and front end and baseband blocks, where you can use some techniques. Okay, that means you can use anti-spoofing antennas, anti-jamming antennas. Okay, and at the front end level, with the help at the front end level, I have told you that you can measure AGC count. By seeing the AGC count, you can see that whether there is any deviation in the AGC count that determine a jamming or a spoofing activity. And at the baseband levels, I told that there are DLL and PLL discriminators. At the output of DLL and PLL discriminator, whether due to spoofing activity, how it is varying and how it will impact. Seeing some thresholds of these values, you can determine whether there is a spoofing activity that is being carried out. This is all at the signal processing level. At the data bit level, after data demodulation, okay, navigation message consistency. That means how the ephemeris across the satellites are, how the navigation bits are varying. So seeing those things, okay, you can see at the data bit level. So at the position level, I have already told you that you compare with other cellular positioning. You also determine through the cellular mobile cellular positioning, and then you determine the receiver position is deviating away from its actual position or not. So these are different ways how you can see or anti-spoofing activity can be carried out. Now, first, spoofing detection methods. So how you detect the spoofing detection? Methods based on RSS, received signal strength. One is AGC monitoring. I told that. One is AGC, automatic gain control or automatic gain count, AGC monitoring. Based on tracking the automatic gain control level of the receiver, spoofing signal increase total received power. Whenever you are receiving a spoofed signal, its power is it is much higher than your original signal. So forcing AGC adjustments. So abnormal AGC values indicate possible spoofing activity. Most effective when spoofing signals have much higher power than authentic GNSS signal. Consider a powerful detection method for signal monitoring anomalies. So AGC count is used as one of the parameter or KPI, that is key performance indicator. When you monitor AGC values, you can determine to some extent whether a jamming or a spoofing activity happens. In case of jamming, the value will come down. In case of spoofing, this value increases. Now, C by N naught. Carrier to noise ratio is used as a measure for signal quality in open skies. C by N naught varies smoothly due to satellite motion ionospheric effects. Under spoofing, high power spoofers can cause sudden C by N naught changes. So the spoofing C by N naught changes. That means whenever there is a jamming, the C by N naught value decreases. When there is a spoofing activity, the C by N naught value increases. But spoofing also happens in two ways. One is synchronized spoofing, asynchronous spoofing. When it is asynchronous spoofing, it is like a jammer effect where C by naught values will decrease. Okay, next one is absolute power monitoring. Challenge for spoofers is that here, see, when you are measuring the power, that means you are seeing the power spectrum, the received power level, not at the C by naught level. C by naught is not a carrier to noise ratio, which you measure in the receiver at the tracking loop level. At the receiver level, minus 150 dBm is the signal, minus 153 dB watt is the GPS signal level at the receiver. Okay, so with the help of variations in this received signal level, you should be able to determine whether there is any kind of spoofing activity being carried out or not. Within plus or within, if the minus 155 dB watt, if the signal level is minus 151 dB watt, suppose received signal level, you can say that it is a spoofing activity, but you should able to determine this power level very accurately at the receiver level, which is very difficult because the GPS satellites are revolving at 20,000 kilometers height at that altitude, and the receiver signal which is being received at from the below the 20,000 kilometers at the distance away can have a rapid fluctuations within this power level, and this is a standard mark, and this can deviate highly depending upon the environment also and the signal propagation effects on the signal. So this absolute power monitoring is a little bit more challenging compared to this CBNOT or AGC, other methods where we can use for GPS spoofing or jamming detection that can be used. And another thing also is that you can see on the right side of this signal, actually the spoofer, for example, the spoofing, if the GPS receiver where the victim receiver mobile is moving and relatively your spoofing device is at a fixed location, and as you move away from the spoofer, as the distance increases, their C by N naught values will decrease. That means the received spoofing signal C by N naught value will come down with respect to the original CBN not value of the signal which you are receiving from the satellites. Okay, so in that cases, detection becomes slightly difficult because of the varying CBN not values. Even if it got locked, suppose initially to the spoofing signal, okay, as the receiver moves away from the spoofer, its value get decreased gradually, where we were not able to exactly determine its spoofing signal. How you can determine and based upon the CPI or not will be something small technically challenging at this point. Okay. Now spoofing detection based on spatial processing. So far we have seen spoofing detection based on RSS, where there is a CBI or not, absolute power monitoring and AGC. Here, next one is spoofing detection on spatial processing multi-antenna receiver. That means this method relies on the fact that real GNSS satellites will transmit satellite signals from the satellite there, while the spoofer usually transmit from one antenna. So he will transmit from a higher side building nearby or from a one location. So taking the carrier differences between the signals, okay, taking the carrier phase difference of the signals received at the receiving antenna in the receiver, we can able to they can find out the arrival of direction of this signal. If all the signal arrivals from one direction, it could be likely due to the spoofer, because in case of satellites will transmit the signals with a geometry which are widespread coming from different directions. So the arrival of direction of the signal is different mostly. So from that you can identify whether it's a spoofing signal or not. Okay. So this is what actually that is unspoofed case and spoofed case for this carrier phase single difference, that what exactly what I have told is the same is represented here. And next one is spoofing detection, spatial processing, time of arrival. Okay, receiver based spoofers must first decode the authenticate GPS signal, then generate the replica signal and introduce unavoidable delay. This delay appears as a misalignment between the spoofed data bits and authenticated data bit boundaries. So, when the actual signal is represented by the data bits, so when you are transmitting the spoofed signal, the data bits transmitted and the authentic signal received also will have the data bit sequence. So they have their own boundaries in transition between plus or minus +1 and -1. In authentic signal, big transitions occur exactly at expected intervals. Okay, extra delay in transitions may cause an incorrect spacing of these +1s and -1s, by trying to see anomaly in this sequence of +1 and -1 sequences of data transmission bits, you can identify is there any kind of spoofing activity being carried out or not actually. And next one is the correlation peak. Okay, so you can find out the correlation peak for the incoming signal, okay, of GPS signal, okay, and able to detect the spoofing for the line of sight receivers, where generally when spoofing happens, spoofing and authenticate signals will get combined. Okay, then you will have a distorted correlator output similar to multipath effect. There are two types of correlators which you can use here to determine the spoofing activity. One is called as the early correlator, another one is called as the late correlator. You can determine a parameter called as delta, which is nothing but IE minus IL by IP. So when this delta is equal to 0, it's a clean signal. When delta is not equal to 0, you can determine that there is some discrepancies in the correlation or distortion in the correlation. So that may determine that there is some spoofing signal in the, so spoofing signal is getting mixed with your authenticated signals. In this way, you can determine at the signal processing level through some spatial processing technique like correlation peak monitoring. So these are the different techniques that which we have can be used using spatial processing, and another one is the RSS based methods. So these are some of the methods that can be used for spoofing detection. And now how do you mitigate the spoofing particularly? So if you want to mitigate the spoofing, there are different techniques. There are three techniques that which can be used. One or 3 to 4 techniques that are there anyhow. A couple of techniques are very much similar, but they have their different ways of implementation. One is the vestigial signal detection, multi-antenna beamforming and null steering, spoofing estimation delay local loop, and spoofing detection, classification and classification. Okay, and cancellation. So these are the 4 techniques that are generally used for spoofing mitigation in the receivers typically. So one is spoofing mitigation technique using vestigial signal detection. In this, you first, what is this vestigial signal detection is that the receiver first tracks the spoofed signal since it is stronger. It then subtracts a locally generated replica of that spoofed signal from the buffered samples. If an authentic vestige remains, the receiver sees it in the residual and knows spoofing is happening. That means, for example, we can say simply in this way that a person is talking very low voice, which is very much authentic. Somebody in parallel is talking with high voice, which is unauthentic. Both combines and get into the receiver. Okay. So that low voice signal remains within this high voice signal, which is not appearing, but your ear is taking the high voice signal. By removing that high voice signal, you can able to cleanly take this low voice signal. So this is called as that vestigial signal detection process. Once the authentic, this happens in these 3 steps or in this way, how it is performed actually. Okay. So so how do you mitigate is that once the authentic vestige is detected, reacquire and lock onto the authentic signal. That means initially you will see that a spoofed signal is coming, which is with very high voice, as I said, or with high power in that case, in our signal processing terms. So that signal when you are receiving, you will try to remove that by generating a replica of signal inside it, and you try to remove it. Okay, and you try to see that it is the spoofed signal is buffered, and internally you generate something, and then we will be reminded with a residual signal, which is nothing but your authentic vestige signal. Okay, so then you try to start reacquiring that signal with the help of that PRN codes. Okay, this is the procedure that typically implemented in vestigial signal detection. Okay. So since the spoofed replica was already first subtracted, the spoofer signal is no longer dominant in this case. So in that way, this is the one of the methods that is being used here. Okay, that means you will look for the residual after removing the actual receiving signal, which is a spoofed signal. Assuming that it is a spoofed signal. If really some residual is remaining, you assume that it is a actual signal, and then you start reacquiring on that. That is what happens in the previous method. Now here, multi-antenna beamforming and null steering. So the basic principle is that here you use a multi-antenna receiver can shape its reception pattern using beamforming. After detecting direction of arrival of spoofed signals, receiver steers a null towards the spoofer. Okay, as I told you, the spoofer will transmit all the signals from one location. Okay, so from one direction, but satellite signals in the above the horizon and are coming from the signal sky in the different directions. You can easily determine with the help of a multi-antenna receiver. You can have the reception pattern of the beam forming, and you can put a null on the direction where you are receiving the spoofing signal. So this is one type of technique that can be used here. And spatial correlation method. Then how do you do that? Actual principle is this, but how do you do that is with the help of spatial correlation method. Compares the phase of correlator outputs across all satellite signals, that is PRNs. PRNs means satellites. Pseudo-random noise sequences are determined by each satellite. So PRNs coming from the same spatial direction identified as a spoofed signal, which I have told you. So spoofed signals are nulled via beam forming. No array calibration is needed, robust against multipath, and needs several antenna and higher computational load. Okay, so these are the things that related to what needs several antennas. Okay, and higher computational load if you want to if you want to do this kind of spatial correlation method. Now, spoofing mitigation technique. Okay, SETLL, that is spoofing estimation delay local loop. Spoofing estimation delay local loop with the help of DLL. Okay, so you try to estimate whether there is any spoofing activity using the DLL. Okay, DLL, delay local loop. There is one thing called as multipath estimation, estimating delay local loop, which uses a principle based upon the maximum likelihood estimation principle to separate the line of sight signals and multipath signals. Multipath signals are signals nothing but that once coming onto the earth will fall onto some building and come to the receiving antenna. Those are called as the multipath signals. So to identify the difference between the line of sight signal and multipath signal, you will use a maximum likelihood estimation technique here, and you will try to use the DLL with this maximum likelihood estimation technique in order to determine the line of sight signal and multipath signal. Now our motive is to find out the spoofing signal. So when you want to determine your spoofing signal, what the algorithm will do is that it assumes MELL. MEDLL generally assumes the strongest peak is equal to authenticating peak signal. With spoofing, fake signal may be stronger, risk of cancelling authenticate signal. That is what we are speaking all through when we are describing about the spoofing activity. So now this spoofing estimation DLL, what it do is that it will internally use a Kalman filter, which will try to predict the authenticating amplitude and amplitude of the spoofing signal. Okay, so with that, it will get to arrive at an initial guess of the amplitudes of these two signals, and it uses a multi-correlator receiver to capture the unsynchronized spoofers, and it will try to determine what are the delays of chips. That means chips means the sequence of zeros and ones of the received signal. Okay, and see how much a delay is there between the chips, and it will determine if it is few tens of chips apart actual receiving signal, then it will identify it as a spoofing signal. Okay, so this is how the basic operation of this spoofing estimation DLL is performed actually with the help of the Kalman filter. Okay, next. So here the standard DLL gets pulled towards the spoofer and gives wrong measurement. So this SDLL, SEDLL or spoofing estimation DLL prevents this by predicting, separating, and cancelling the spoofed replica, keeping the authenticated signal intact. So scenario is spoofer transmit a signal slightly shifted by 0.5 chip delay. Okay, that means that exactly it is not correlated with the incoming signal. It is between difference with a point chip delay. Okay, and the phase offset is around 45 degree and 3 dB stronger than the authentic signal. These are the characteristics of the spoofing signal which I am telling. So the standard DLL confused by the strong spoofer shifts tracking point. So it will shift its tracking point. So leads to a large code error of 0.4, 0.43 chips. Big position error. So what this spoofing estimation DLL will do is that it correctly identifies the authentic path with the Kalman prediction, because it could authenticately determine the power of the authentic signal and the spoofing signal. It cancels out the spoofed signal, and the final error will be very less, which is 0.016 or very small, almost unaffected. I only just depended a typical value for understanding, that's all. To avoid mistakenly discard the real one. So the Kalman filter predicts the expected authentic amplitude used as a guide, so the authentic signal is not cancelled. So this is one of the techniques that is used, spoofing estimation DLL actually. So next one is okay. Now you have identified, you have to mitigate. Mitigate means you have to remove that signal. Okay, so what is a chip in GNSS generally? Just I want to determine. GNSS signals uses spreading codes like CBA codes +1 -1 +1 -1 sequence. Each bit is of parent code is called as a chip, and one chip length is 1 by 1 by 1.023. That means it is a C by a code. Course acquisition code frequency is 1.23 megahertz, 1.023 megahertz. If you convert into nanoseconds, it is 977 nanoseconds. So the distance of one chip is approximately 977 nanoseconds into velocity of light. That gives you 293 meters per chip. One chip will lead to, if there is I told that if a spoofing signal is transmitted with 0.5 chip delay, 1 chip delay, like that, if it is a 1 chip error, suppose it is 300 meters ranging error, a spoofer sent a fake signal delayed by 0.5 chips, means approximately 146 meters shift. Standard DL gets confused and it will try to cause around 0.43 chip error, which is approximately 126 meter error in the range. But this ACDLL detects and cancels the spoofing error, reduced to 0.16, which is approximately 4.7 meter error. That means you may able to estimate the spoofing signal, discard it, but still there will be some error that will be introduced when it combines with the actual signal. So which is very much reduced through the mitigation process, even though it is not 100%. Okay. Next, there is another method called as spoofing detection, classification, and cancellation method. So this is also a three-stage technique. Here what they do is that they use the different techniques for detection, spoofing detection, like AGC monitoring, spectral analysis, equation level detection. Okay, each signal is acquired only if it is beyond some threshold level. Okay, so all satellites are being transmitting signals at one location. You may see some 10 satellites, but all not 10 satellites can be acquired, because at the receiver side, when it comes to the receiver, what is the threshold of that signal? It is determined by equation level. If it is beyond certain level, only the equation can happen. So so these are the three techniques that I told how AGC monitoring can be done, how we can do the spectral analysis, okay, equation level detection. So all these things will help to determine the spoofing detection block. Okay, so this is the spoofing detection block, and another one is called as the spoofing cancellation block is there. Okay, and spoofing and authentic PRN classification. What is the spoofed signal? And another one is what is the authentic signal? Okay, and how we can cancel it, and first here you are classifying and you are canceling finally. So these are the three steps that are carried out in this SDCC, spoofing detection, classification, cancellation technique. Detection is based upon AGC ADC monitoring, structural power analysis. Okay, another one is equation level detection. Flag raised if spoofing indicators are found. With the help of this detection, you try to identify it is a spoofed signal if there is any spoofing. Now, spoofing classification. That means here the classification between the spoofed signal and the authentic signal is carried out. All detected signals will the combination of authentic plus spoofed are tracked. Receiver requests small antenna movements to detect the motion. Classification method computes pairwise correlation between the signals. Okay, so between different satellite signals, a correlation is carried out. And if there is a spoofing group, they are highly correlated, because all the satellites will be transmitted with a high power. But in case of unauthentic signals which are received from the satellite, the correlation among the satellite signals will be less. So with this, you can identify whether it is a spoofed satellite signals or authentic group signals, authentic satellite signals. You can determine here. So in this way, you will try to classify. One is detection, another one is classification, and finally is the cancellation. So here what happens is that raw IF samples plus spoof PRNs plus tracked parameters. Okay, continuously track both spoofed and authentic signals, reconstruct the spoofed signals. That means code offsets, Doppler phase, and amplitudes of the spoofed signals, and subtract spoofed replicas, because you are now understood what are the spoofed signals from here. So same signals you try to regenerate them internally, their codes and Doppler phase amplitudes. You try to remove them by subtracting, then you will get the actual raw IF samples of original signals. So this is how the functionality of this technique is performed. So each mitigation technique has its own complexity of implementation and the effectiveness in detecting and mitigating the spoofing activity. So this shows that, and when it gets the effectiveness, multi-antenna null steering, because you put a null to the spoofer antenna side so that you may not receive the signals, so it is highly effective. and this SDCC will do multiple tasking. So this is highly effective. Okay, and complexity also medium in both the cases actually. So these are the approaches that can be implemented for mitigating the spoofing. So GNSS spoofing, you understand, it is manipulation of GNSS measurements to make position estimation unreliable. Receiver algorithms employ. Okay, we are getting out. So mechanism for deviation or spoofing, we can overlook at those parameters at the equation level, at the tracking stage. These parameters can be looked for spoofing activity. And finally, GNSS spoofing detection parameters at different stages. These are some thresholds that can be used to determine if there is any spoofing activity or is happening on these parameters. Okay, now GNSS jamming. Jamming can happen because of the signals that are coming from nearby TV transmitters, harmonics, ultra wideband transmitters. There are specifically GNSS transmitters that are widely available in the market, commercially available in the market. This is the website from China that where they produce many type of jammers actually, even for the Wi-Fi signals or mobile signals or for the other signals like our GNSS and everything. There are specific jammers that are available which can be used, which are coming at very low cost and used by people to receive the GPS signals sometimes, which is a crime also. So just jammer transmit signals like crib jammer, pulse jamming, continuous wave jamming. There are different types of jammings that can be performed. Okay. Recently in 2023 and also in recently now also in 2025, you can see that these are the places where the jamming is very high actually. There are different incidents of jamming that is happening around the world. Okay. Unintentionally or intentionally. Intentionally doing is a crime. Unintentionally it happens because of different types of electronic systems that are transmitting signals at nearby frequencies or within the bands of GNSS because of those electronic devices that are generating some harmonics like that. So this is the website that can show you how much intensity the jamming is there at different locations. Okay, the high red is about 10% of jamming, medium 2 to 10%, and 0 to 2%. These are the areas. So here you can see at the Norway and Finland, other areas, you can see that the jamming is very high actually. So there are areas in even if you see our India, it is like it is medium. The jamming effect is medium actually. So this in this way the jamming activity is getting highly intensified around the world, and there is the need for effective jamming detection and mitigation techniques that have to be implemented actually. So there are different types of jammers: crib jammers, FAW2 jammers, pulse jammers, and continuous wave jammers that can be used. Okay. So each jamming has different kind of effect on the signal, and you should able to remove this jamming effect actually if it is in the band. In band jamming suppression is very difficult because out of band jamming can be removed by using a baseband filters. In band jamming, you should specifically understand what is the narrow frequency range at which the jamming is being happening. So you should be able to use a specific type of filters. Those are called as adaptive notch filters that widely used in the receivers of GPS receivers like Septentrio, like that, which they broadly use different types of an adaptive 3 or 4 adaptive notch filters will be used so that it will try to identify at what narrow frequency there is a spike that is introduced in the spectrum, because most of the GNSS signals are below the noise band, widespread, because below the noise floor, and the noise floor is widespread on the GNSS bands. If any spike is detected, we will try to see what frequency that spike is introduced, and they will use the notch filter to remove that. This is how the actual jamming is removed. There are different types of jammers that are used actually. There are cigarette light jammers, crib jammers, multi-band jammers that are widely used in the market, and these sites can give you the information more actually. So what exactly happens to these DLL and PLLs if you are jamming? See, as long as there is no jamming, the signal, the DLL, PLL outputs will have a small variations within their with the code discriminator outputs actually, and carrier discriminator output. Whenever the jamming is there, there will be a random variation or fluctuations in this. By seeing the beyond whatever the thresholds that it is crossing, we can determine whether there is a jamming activity or not. Okay, and also IF samples which have a Gaussian distribution will have a random distribution when there is a jamming effect. If you take a chi-square test on these things, you can determine jamming. At the equation level, instead of having one spike to when it is to determine the cross ambiguity function, determine determines a one spike here. Actually, to determine, you will have multiple spikes that determine, and there is a jamming activity that is happening. So like this, based upon the measurements, you can understand when you see these measurmental variations, you determine whether there is a jamming or not. Even sometimes position will vary high, where see the position suddenly goes to 20 meters or 30 meters or 40, 60 meters like that when there is a jamming activity. When jamming activity is increasing, the C by N naught values will decrease and your AGC count will decrease, as I showed you initially, and there is a change in the positions that leads to higher values because of the jamming. Okay, so by observing these parameters and having some threshold, many of the techniques that are provides this kind of thresholding approaches like that actually on these parameters to determine whether there is a jamming activity happening or not actually. So GNSS jamming is a challenging and the main indicators are C by N naught. Okay, sometimes the carrier can track failure because the C by N naught values go below 30 dB heads. Okay, because of jamming. And if it goes to 28 dB heads, the carrier start tracking fail and completely it will get lost when it reaches below 24 dB heads actually. So, and also your AGC count will decrease from 8,900 to near to zero. This AGC count is not a specific value here because typically AGC count, actually in case of C by N naught, it is from 50 dB heads to 0 dB heads if it goes down like that. From AGC count is 8,191 to near to zero, it is an U blocks receiver. If it is a septenary receiver, these counts will vary actually. Okay, and the meaning of interpretation also will slightly vary based upon whether it is strong, it can decrease or increase depending upon the situation of the receiver AGC count, how they build the RF front end actually particularly. Okay, so again DLL and PLL outputs. The DLL means delay local loop output is determined with the help of chips or in meters. Okay, and PLL output is determined discriminator phase error. PLL will determine phase error, DLL will delay local loop or discriminator chip error actually. So the chip error 20 to 50 meters is generally noticed in continuous wave and narrow band interferences. And when it is a phase local loop, actually 20 degree to 50 degree variation is there in the phase shift or in phase error because of strong jamming actually. Okay, so these are typical values from different authors, one who have reported this kind of results actually. And their interpretations with respect to DLL and PLL error when specific type of activity of jamming is happening, like clip jamming or a continuous wave interference that is happening at what rate and at what free. If it is at minus 130 dB, what actually if a clip jamming is done, chip jamming is done, what are the DLL, PLL values, how they are varying. Okay, these are some insights that have been derived based upon this jamming and spoofing like that. So this is a typical table that I can show you that represents how the decrease in different parameters can happen because of the jamming and how much values will get deviate. These are not standard values, but typical representations that we can derive from the inferences that we had from the literature or through experimentations if we can carry out. So these were the values that you can notice that determine not changes in the AGC, C by naught and DLL, PLL errors, how they vary, at what rate they vary, then how we can correlate if a AGC count is decreased by 80%, if it is 30 to 50%, a mild jamming incidents are happening, or a moderate jamming is happening, or a severe jamming is happening. So as I told you, the AGC counts also will vary to the receiver. Okay, and how their representation is. Okay, 0 to 821 high AGC count value is A191 strong signal it represents. With 0 represents a low AGC count value means weak signal you are receiving. Okay, because of interference or any other reason. But in case of septentrion, okay, low AGC count value determines strong signal, that means 0, and 1023 will determine the weak signal. So here there is some discrepancies. The not discrepancies is that the way they build the RF front ends and the way they represent these values, actually receivers. Okay, and these sites I have provided. Okay, these sites generally give you, that means the notch filters, how they are applied actually to determine to suppress in the septentrion receiver. This is one of the site you can go through. And if you want to know what happens to if it is a clip jamming happens on the signal, how it can show you. So these are the things. So these are some of the references. Before that, just I will show you once. So if there is a crypt jamming, these are the types of jammers that can be used or procured from the websites. 10 milliwatt, okay, 300 milliwatt, 4 antennas are there here like a jamming unit. So this is the crypt jamming that can happen on the signal. Okay, so the signal power increases. That means not the signal power increases, the interference get added. It shows an increased signal level power. You have to mitigate it with the help of a notch filter, and you should able to retrieve your original signal. Okay, so generally these septentrion receivers will use the notch filters to mitigate the jamming effect. Even though it is a wideband, still they will try to reduce it. Okay, so this is how this technology works and the importance of this technology and various techniques and methods that have been developed. And in the present state of art, we're using the deep learning and machine learning algorithms like SVM, CNN, LSTM, BiLSTM. There are different approaches being employed by different people, probably for classification of different types of jammers in one way method. And that means from the data they from the measurements whatever I have seen I told you is maybe the power spectrogram. They will take the spectrogram of the signal and determine what type of jammer is used for jamming, whether it is a crypt jammer or it is like that, because machine learning techniques can classify. Okay, and so machine learning and deep learning techniques are widely used for that, and also to determine whether it's on the signal parameters changes like CBN or DLL values, PLL values, they will pass through the deep neural network as an input after scaling and data to determine whether any jamming activity or spoofing activity is being carried out, not by the variations that can be noticed in these things. So this is how the state of art is going towards using these advanced algorithms like deep learning and machine learning on these parameters. But this is the basis where actual parameters that have to be considered if you want to determine your jamming and spoofing activity. Okay, so with this, I try to end my lecture, and if there are any questions, you can come from your side, please.
Yeah, do you have any questions you can ask?
Sir, for your informative section, Satyanarayan sir has given insightful lecture on global navigation systems. These systems are now critical for navigation, communication, transportation, defense, and even financial synchronization. However, their open signals are vulnerable to jamming and spoofing attacks, which can disrupt positioning, navigation, and timing services with serious consequences. SAR has provided us with deep insights into how advanced signal processing techniques such as adaptive filtering, antenna array processing, interference detection, multipath resistant tracking, and machine learning based classification can strengthen the resilience of GNSS systems. I sincerely thank our distinguished speaker for explaining these complex challenges and solutions with such clarity. Your insights has broadened our understanding of how resilient GNSS technologies are being developed and how they will shape the secure navigation system of the future. Thank you, sir.
Yeah, thank you for the opportunity given for sharing the thoughts on this GNSS jamming at spoofing. Thank you.